Hello there, my earth science students. Dr. John Shaggy here. Thank you for all your patience with what's been going on this week of all the craziness with my son being out as a close contact for COVID. We'll get everything worked out. When I get back, we're going to do some labs about earthquakes that are more of an adventure. And we have some other labs we can get caught up on. And I know people would rather do that than hear lectures, especially lectures over Zoom or whatever this recording is. Um, Today I'm going to finish up the so-called third day of Module 2 lecture. We might get through all of the fourth day one. I'm not entirely sure because I'm going to skip around a little bit. So anyway, so if we're going to go on to that third day of Module 2 one, I'm over here at slide 37. Let me zoom this up here. Fantastic. And where we left off last time was the science of seismology. Seismology is studying earthquakes and understanding earthquakes. Today, we're going to be talking about the kinds of waves that earthquakes create. These are the ones that actually not only create the damage, but also how we figure out in retrospect where the earthquake happened. And it says here that we're going to study the principle of the seismograph or the instrument, which is called the seismometer. I think we're going to keep it a little simpler than that, but we'll focus on a few things here. Like, for example, I usually try to teach how a seismograph, the instrument that measures the seismic waves, I like to teach how that works. But I think this year we won't worry about that because of the under the circumstances. But when we're talking about a seismograph, you probably have seen these kind of charts before. Um, as the earthquake waves go by, there's like a little pen that draws the waves as they go back and forth across here. Um, this is a piece of paper on a drum that's slowly turning, and there's a pen over here that is slowly moving from left to right across the drum here. And then when an earthquake happens, you can kind of see the wiggles as the waves go by. So the piece of paper has, that piece of paper has gone around like 20 sometimes or already. Usually one turn of the paper is an hour. Anyway, but these wiggles in the track of the seismograph are what we're interested in. They're measuring different kinds of earthquake waves as they go by. So the chart says here the chart's called a seismogram. I thought the chart was called the seismograph. Okay, well, that's fine. I wouldn't be trying to make a tricky question about that. But it is important for us to spend time learning about the different kinds of seismic waves because this is going to be important for the lab activity where we learn how to find where an earthquake occurred. Broadly speaking, your book is going to tell you that there's going to be two different kinds of waves. There's going to be these so-called body waves, which are the waves that uh, hold on just a second here that actually move through the earth, and there'll be surface waves that move across the surface of the earth. And then we're going to sort this out here that there's going to be two types of body waves that move through the earth, the primary and the secondary waves, which go with these by these names P waves for primary and S for secondary. Now I know this is kind of a lot, but I hope that the slide here is helping you understand the structure here. There's seismic waves, and there's two kinds of them: body waves and surface waves. And there's two types of body waves: P waves and S waves. There are different kinds of surface waves too. Some of these waves that move along the surface of the earth and cause the damage, move rocks and houses and bridges and stuff up and down, and some of them move side to side. And they are, in fact, different kinds of waves that move through the rocks. But that's actually kind of self explanatory. I mean, there's nothing tricky to the names about this or anything like that. I'm not too worried about surface waves. Students usually tend to understand that part pretty well. More complicated is this business of the body waves. There's two different, let me back up here for a second. So, like I said, the kind of waves that move through the body of the earth, not along the surface of the earth, can either be primary waves or S waves. And the difference has to do with how they're causing motion and how fast they are and how strong they are. The P waves are what are called push pull waves, the primary waves. The movement is going to be like back and forth. So if the earthquake is, to your east, you're moving east and west, like your motion is pointing toward and moving away from the where the earthquake was. But the S waves, the secondary waves, a good way to remember that is those are the shake waves. Those are the waves that are moving rocks, buildings, houses, whatever, side to side as they go by. So, like, for example, if the earthquake is straight to your east, you're moving north south as the earthquake waves go by. Don't worry about this stuff in red about whether they travel through solids or liquids or whatever. We'll chill out about that this year. But there's an important difference between these three kinds of waves. The P waves move the fastest. The S waves move somewhat slower, and then the surface waves, remember P waves and S waves are types of body waves, the S waves move the slowest of all. And it's going to be the difference in time between how long it takes P waves to get to you versus how long it takes S waves to get to you that's going to help to your seismometer or whatever. That's going to help us figure out how where the earthquake occurred. Again, it's going to take a lab to demonstrate that. Once you see this in a lab, you'll be like, "Oh, that makes perfect sense." But the P waves and the S waves travel at different speeds, and so we can use the difference between when they get to our seismometer to tell us how far away the earthquake happened. And so we can figure out where the earthquake was. And so here you kind of get a sense of this sort of story here. Here's the hypocenter of an earthquake. If we have one seismometer some distance that's not that far from the hypocenter, the P waves got there fast, but the S waves didn't get there all that much longer afterward. The distance, the length of time between the arrival of the P waves and the arrival of the S waves isn't very big. The earthquake is not far from seismograph 1. Whereas, like for seismograph 2, the P waves arrived, and then it was quite a few more seconds before, actually a couple more minutes, before the S waves arrived. It took a fairly long period of time between the arrival of the P and the S waves, meaning that the earthquake was fairly far away. And in fact, I'm saying fairly far. We're going to be able to quantify that to like a number of miles kind of thing at the lab. We don't need to worry about right now for like which ones have larger amplitude and stuff like that. We can chill out about that. All right. So we will do a whole lab about P waves and S waves and seismology when I get back. That's not going to be a big problem. Let's move over here to presentation 4 for day 4 or whatever this one's called. And once you get past the review slides here, we're just going to be learning about where do most earthquakes occur and some forecasts and predictions and so on as to how earthquakes work. We actually had a little bit about this before I left. There's really two earthquakes that happen lots of places, right? I mean, we have earthquakes even in Indiana. You can see there's lots of little individual dots here representing earthquakes. But there seems to be two main patterns to the earthquakes. One is this circum-Pacific belt of earthquakes that's all around the edge of the Pacific Ocean, where the Pacific plate is subducting under continental plates, like the Asian plate, the Eurasian plate, and the North American plate, and the South American plate. Or we have this alpine Himalayan belt where Africa and India are pushing into the Eurasian plate. And I'm not going to worry this semester about the difference between like the types of faults that occur on each of these two different belts. But basically, there's two main parts of the world where earthquakes happen. And I think if you think about what you know about in life about earthquakes, they are in California, Mexico, South America, Japan, places like that. I mean, these parts of like the Middle East and the Himalayas and so on. I mean, this sounds like where you think most earthquakes happen, but that certainly does not preclude the fact that plenty of earthquakes do happen in other parts of the world. So, like, if we're focusing on America, what about this whole area that's east of the Rockies? Well, we certainly have several very big earthquakes that have happened in U.S. history east of the Rockies. I don't know exactly why they're ranked here from weakest to strongest. I'm not quite sure why that. It seems like it could be more useful the other way around. Um, but for example, here this one in New Madrid, Tennessee. Hold on, back up here is one of the strongest earthquakes in U.S. history. You don't normally think of New Madrid, Missouri as being a big area for earthquakes, but in fact, one of the biggest in U.S. history happened there. A big one in Charleston, South Carolina. Again, you're not really a place that you expect earthquakes. I mean, that would be a big earthquake in California at 7.3 magnitude. Again, here's just a few years ago, there was one in this Wabash Valley seismic zone. This is the one. You guys were super little when this one happened, but this is the one that happened when my wife happened to be visiting family out here. We were living in Nebraska at the time. And again, I mean, you definitely felt it. There was some small damage in Evansville, things like some chimneys toppled over onto roofs and things like that. But I mean, 5.4 is not that's not a small earthquake. In fact, have even been more recent ones. I happen to have a screen capture from the Indiana Geological Survey about one that happened about 4 years ago. I mean, this is only a magnitude 3.8, but this one could be felt in Indiana, absolutely. And there's been one more recent than that I can't seem to find my screen capture of. But earthquakes certainly do happen around here. In fact, that's why we need to think about earthquakes in Indiana. They all happen along this piece of a fault called the Wabash Valley Seismic Zone. This is part of that whole story about the rifting of North America that happened about 1.1 billion years ago, where the North American plate tried to tear itself apart. This is part of where that fault started happening, where the continental plate started to rift. Now, it's actually a very difficult place to study rifting and faults because it's under a very thick layer of soil. The soils in this area are several hundred feet thick. It's not like the fault is exposed. That's an awfully thick layer of soil to do like any kind of digging and expose it so you can study it. Pretty much it has to be studied with things like ground penetrating radar and things like that. We can't actually go and look at the fault directly. Um, so it's a difficult area to study, but we know that it is a place where the North American plate tried to rift along this area between about New Madrid and the Wabash Valley, and it continues actually to try to shift. It's very very slow, even compared to most continental plates. Remember, continental plates move a few inches per year. This is at like 1 to 2 millimeters per year. I mean, this is like 10 times smaller than that. But it does continue to try to have some deformation along the zone. The plates are trying, the plate is still weak there and trying to shift. And so we certainly do get earthquakes. Now, both the EVSC and Ivy Tech make it explicitly a goal of the class that we're supposed to talk to you about how to be safe during an earthquake. I think that's a little bit strange, but on the other hand, actually, most of the stuff that they teach you in here about how to be safe during an earthquake is actually good general advice for how to be safe during a natural disaster, whether that is a tornado or a flood or an earthquake or whatever, or a man-made disaster like a terrorist attack or something like that. Honestly, most of this advice is pretty darn good. So, like, for example, long before there is an earthquake, most of this advice is actually pretty good. Like, you should have a disaster kit in your home. You should have things like a few days worth of food in your house. You should have some supply of fresh water. For example, down in our storage area in the basement, we always have some cases of water that, like we use when we go camping or something like that. We just take a case of water with us. But it's actually also there just in case, there would be some disaster that we didn't have access, the water wasn't running at the house. You should always have a list of your emergency phone numbers. Um, Again, everybody keeps that kind of thing in their phone now, but then again, if the phones are, if you don't know if you run out of the house during an earthquake or you run out of the house, run into the basement during a tornado, you might not have your phone with you. So having some kind of list, but on the other hand, that's difficult because you're going to be like, panicking. You're not going to go get your list. Um, this is actually an important one. You and your family should have an idea of a place that you're going to meet away from the home after a disaster, like by the front yard tree or on the sidewalk or whatever. It's often a panic after there's like a fire or a tornado is people can't find each other even though they're close to each other. Some of the family evacuated to one part of the yard, or some evacuated to another. Some are in the front yard, some are in the backyard, and nobody knows where anybody is. Are they still in the house? Hey, that's my 8-year-old. Hold on just a second here. I'm gonna pause recording for just a second. All right. Again, it doesn't really matter whether it's an earthquake or a tornado or a fire or a flood. Adults need to know how to do things like turn off the water to the house, especially the gas to their house, the electricity if necessary. These are all really good things to know in general about being prepared for disasters. Same with especially when kids are little, securing heavy furniture like bookcases or hanging televisions, so that they don't tip onto people in the event of an earthquake or a fire, or well, not so much a fire, but a tornado or something. This is all really good advice. Now, of course, during the earthquake, these are more specific advices about what to do during an earthquake. In general, you want to take shelter under something sturdy, like maybe a table or something like that. Um, Sometimes people think that's pretty weird. Wouldn't you want to not be under something sturdy and heavy? But the thing is, the most likely types of damage is some minor damage of things falling, like maybe the drywall falling from the ceiling or the light fixtures falling from the ceiling. Well, the table is certainly going to protect you from things like that. I mean, obviously, the whole house collapses on you. This might not be enough to protect you, but you know, things falling out of the cupboard, the light fixtures falling, something like that, the table will protect you pretty well. Um, if you're outside, obviously stay away from things that could fall on you. Again, I'm not quite sure how much time you would have to respond to things like this. Um, if you're in a building or structure, never go outside. I'm not really sure what that's all about. Other than maybe they're thinking getting out of the building isn't very safe, like, running down the stairs and stuff to get out of the building isn't such a great idea. Their advice that they have for after an earthquake also seems like good advice for after a tornado, after a fire, after a flood, etc. Terrorist attack, whatever. Um, in the case of earthquakes, of course, you need to be worried about aftershocks, the small earthquakes that can happen, for days or weeks afterward. They said even years after, I don't know. This is something that a lot of people who live in earthquake areas are very afraid of. They often, after an earthquake, don't want to go back into the building wisely because they know that the building is now damaged, and even a relatively small earthquake will now cause, an aftershock will now maybe cause the remains of the building to collapse. Obviously, don't use the elevator after any kind of natural disaster. You should monitor your local news, radio, or social media for information. Again, it depends on whether or not your internet access is working. That's why sometimes it's a good idea to have something like a radio. Let's see. Phone calls should be used for emergencies after a disaster. Yeah, don't just be calling everybody you know to see how they're doing. Did they feel it, etc. Um, Even under the best of circumstances, local phone calls, a certain percentage of the time the call doesn't go through because the lines are busy. Just after an earthquake or a fire or a tornado or a flood or something like that, the phone lines tend to be jammed. And keep in mind, if 5% of local calls don't go through, it's not the end of the world until you think about the fact that that probably means 5% of 911 calls aren't going through. All right. So don't use the phone call just to be calling and checking in on people. They'll be fine. Save it for emergencies. Would we know if an earthquake was coming? Well, it kind of depends on what you're asking there. Um, we talked briefly the other day about the fact that short range predictions, like trying to warn about an earthquake that's going to happen a few hours a day in advance or something like that, by trying to identify earthquake precursors, the things that happen before an earthquake, that has never been shown to work at all. The animals don't know that there's going to be an earthquake. There's not some buildup of electricity. There's not strange lightning. Just the other day, there was a minor earthquake in Acapulco or Cabo. I can't remember, one of those places in Mexico, and there was all this stuff on social media about earthquake lights happening before the earthquake. There's no such thing. Okay, there are no precursors to earthquakes. The processes that are happening to trigger an earthquake, or as an earthquake is happening, happen far below ground, deep in the lithosphere. Many earthquakes occur 20, 30, the hypocenter is 20, 30 miles below ground. Um, that is not, we don't have any way to be measuring what's happening down there. Dogs don't know what's going on down there. Gases in the atmosphere or whatever. The birds don't know about what's going on down there. Uh, whatever's happening leading up to an earthquake it's buried under miles and miles of rock. There's no precursors that we can measure or whatever here at the surface. There certainly is such a thing as long range predictions, but these are things that are estimating the likelihood that an earthquake of a certain magnitude will occur on some time frame. Like, what is the chance there'll be a magnitude 6 or greater earthquake in the next 30 years? Or what is the chance that there'll be a magnitude 7 earthquake or greater in the next 100 years? That kind of thing. Those certainly are a real thing. That's how we know a lot about, like, for example, we're still expecting the big one, a big earthquake to happen along the San Andreas Fault. But obviously, this is not really something that helps you and me make day to day decisions. This is more used for like planning purposes. When they're planning the construction of a new hospital, or when they are planning the construction of a new bridge, they need to know what is the likelihood that a certain magnitude of earthquake will happen during the useful lifetime of the bridge, so that they know how strong to build it and so on. This is not useful to you in your day to day life, like, you need to store a certain amount of water in your basement because there is a 50% chance of an earthquake in the next 30 years. I mean, this is not useful to people in a day to day life. This is more of a civil planning type thing. Typically, the way these kind of long range predictions are done is by looking for what are called seismic gaps in the paleoseismology record. Paleoseismology, what a great word. Paleoseismology is the study of earthquakes in the past, where we can use rocks and debris and so on to study, and the historical record for that matter, to keep track of how often earthquakes happen in a particular location. And then we can see, oh, I see an earthquake of this size tends to happen every 20 to 40 years. And so now we know, okay, if we haven't had such an earthquake in 60 years, we're kind of overdue for one. That kind of thing. We're looking for the gap, how long it is between earthquakes in the historical seismology record, the paleo seismology record. Paleo just means like historical. So, what can we do about earthquakes? This is not the kind of disaster we can really prevent, right? I mean, we don't have any control, in contrast to, say, flooding and so on, where we have some measure of control of, like, with dams and drainage projects and things like that. In contrast to that, we really don't have any control about what's going on with earthquakes. But actually, there are things we can do, like be prepared. All of these kinds of things that we talked about how individuals can be ready for an earthquake, like having a list of emergency contact numbers, having a plan with their family as to where they're going to meet after the earthquake, having a few days' supply of food and water, whatever else was on that list there. A radio with batteries, that kind of thing. That all stuff at an individual level really does help. Not to mention the way communities can plan, which kind of fits under that category of building properly. Um, Places that have a lot of earthquakes tend to have really impressive building codes that are that really do work. I mean, you'll notice that places like Los Angeles or Tokyo that are right there on the circum-Pacific earthquake zone and get a lot of very large earthquakes, they still have things like skyscrapers and stuff like that. Buildings can be built to survive a surprisingly big earthquake as long as you build them properly. We can build our infrastructure properly. We can have roads that are appropriately built, especially bridges and things like that, so that emergency vehicles will be able to get through when there's been an earthquake, etc. These are good strategies that help save lives when earthquakes happen. The other thing is to have warning systems. Now, I think in the recording the other day, we talked a little bit about warning systems. These are the systems that detect when an earthquake waves past the sensor and they radio ahead to tell you that earthquake waves are coming. So, for example, if there was, I don't think Evansville has such a system, but one could envision that maybe Ivy Tech would put something in like this, where like maybe they would have sensors out by the New Madrid, the Wabash Valley seismic zone that would notice when earthquake waves happen, and then it would radio ahead and set off an alarm at Ivy Tech that would say, "Hey, an earthquake is happening." And it takes maybe 20, 30 seconds for the waves to get from the Wabash Valley seismic zone to Evansville. And that would give you 20 or 30 seconds of time to get under tables or whatever it would take to be safe. And now I don't think we have anything like that in Evansville because we just don't have that many earthquakes. But this is very common in California and in Oregon and Washington, where they have a fair number of earthquakes and a very high population. The kids, just like we have tornado drills, the kids in school have earthquakes drills where the alarm goes off and you get under your desk because you may have only a few seconds, you might have as much as a minute or something, but you have a certain amount of time before those earthquake waves will get to you, and the alarms are going off. These systems save lives every time these things happen. Again, just thinking that earthquake in Mexico the other day, there was some stories about how Mexico City does have such a system, and in fact, the alarms went off. Now that earthquake happened in the evening, so kids weren't in school, but places of work and places, restaurants and stuff, alarms went off because there were earthquake seismic waves coming, and people were able to get under tables or whatever was secure in their location to protect their lives. So these kind of systems absolutely do work. Um, like in the Seattle area, it was branded as Shake Alert. I wouldn't worry about that. All right. As far as I'm concerned, that's enough new material for today. We kind of just skipped around a little bit and talked quickly about this. Um, One thing that you can do, this is an old presentation, so we're not doing this lab on Thursday, but when I get back, we're going to do a lab about earthquakes. And in order to do that, if at all possible, you should install Google Earth Pro on your laptop. Now, I don't think the Chromebooks can do this. You can try, but I think that things are locked down in such a way that you can't install apps on an EVSE Chromebook. But if you have your own laptop that you're bringing to school, a PC or a Mac or whatever, even I think your own personal Chromebook, if you have that, go to the website. Just Google the site Google Earth Pro, not Google Earth, Google Earth Pro, and install that on your computer. That'll save us some steps. Okay, Google Earth Pro is a pretty cool version of Google Earth that it's free, and it will help us. It has certain features that will help us with the earthquake lab. All right, I think we're good. Any instructions about any assignment or anything like that you have will be waiting for you over on Google Classroom. And I know this was kind of a rushed thing, but I appreciate your time, and I will see you when I get back.